let's move to lecture 3, B part 4. Part 4 is properties of the Hamiltonian. The lecture 3 is symplectic geometry and Poisson's bracket. Poisson's bracket is, we also derive the Lie bracket. So this is a kind of a Lie bracket, but this leads differently, okay? But all the properties of the Lie bracket is applied to the Poisson's bracket, you see. So, from the previous lecture 2, for I is equal 1 and 2, you see, this is a pseudo-gradient of H the function of Z, and this is, just attentional, you just see here, you see, this is exactly what I copied from lecture 2, okay? That's exactly this. And this just to call your attention that H is function of Q, which is function of T, and P is also function. This is a generalized coordinates, and this is momentum, P function of T. That's why we obtain Q dot and P dot. You see, Q dot and P dot are the derivative of Q with respect to T, the time. You see? Now, for the autonomous system, you see the Hamiltonian is function explicitly of the time. Okay? This is not explicit on the time, you see, as you pointed out over here. So I said, just copy this. This is the final of lecture 2. Okay, it's just over here. That's why I separated. Now you are moving to the lecture 3, actually from here. You see, the Poisson's bracket, okay, let A, QP, and B, this is QP here, also QP, in this order. See? B2 is smooth function. In general, in the literature, we call this little f and this little g, okay? But in this here, I just set A and B. So, this is a 2 degree of freedom, okay? Degree of freedom is important concept. This is a 2 degree of freedom phase space with coordinates Q and P. Attention now, Q is function of T and P is also function of T, as you pointed out, okay, this over here. Now, then we define, attention now, define the pseudo gradient as the column vectors. You see, this is column vector, column vector. This is exactly analogous to the H over here, capital H. You see? So this I call, this is a gradient, pseudo gradient of A, the function. This is pseudo gradient of B, which is a function. So gradient of a scalar, it is a vector. See? Now, recall the canonical symplectic matrix J, so that for any vector V belongs to R4, okay? And then JV, the product of this matrix, attention now, this J in general is a 2n by 2n, okay? The dimension of this J over here is even, always even dimension. And V is a vector, okay? Then we implement this over here, just swapping and sign flip of the position of the momentum. You see also, this over here, it is in the lecture 2. Instead of A and B, there is H. You see, also this is same. So now you are moving to step 3, definition of the Poisson also called curly bracket. Poisson's bracket or curly bracket is the same. You see, this is a curly, okay, instead of a bracket, as in the Lie derivative. I'm sorry, in the Lie bracket. So this is a curly, in this case bracket. Definition. Attention now. This is gradient of the transpose of gradient of A. Okay? By definition. Definition, there is no question. You have to assume. Then this, the J, okay, this is a gradient of B. This, attention now, this belongs to the C infinity. What is C infinity? You see, you take the first, the second, the third, the fourth derivative. The function, the result are all smooth functions. That's what we call C to infinity. That's a phase space. Attention now, phase space is also called cotangent space, as we emphasized in previous videos. So then I can write, instead of write partial derivative here, you just set A, you see there's a Qi, A Pi, you just substitute this partial derivative here. Likewise, BQi and B Pi. You see, that's a denotation, okay? Now, explicitly I is equal 1, 2, the expansion, you see, attention now, you see, when you write I here is a dummy indices, dummy index I. That's I, they expand, this is for I, in this case is equal 1, our I is equal 1, and I is equal 2, you see? So as I said here and I say here, for I is equal 1 to n, you see, adjust the expansion is the curly bracket A and B, is A Qi and B Pi minus A Pi B Qi. You see, you just, that's quite easy, okay? Attention now, this J, okay, use a matrix, geometry in this case, is the symplectic matrix, okay? Remember that I2 over here, you just come over here and see this. See, this is I2. And this here is minus I2. And these are the zeros, and these are the zeros. So I just plug from this, I plug over here. Now, then I just, you see, I multiply this 4 by 4 matrix times 4 by 1. That's a column. This is, the result of this is 4 by 1. Attention, 4 by 1. This is 1 by 4. 1 by 4 times 4 by 1, it is a function, it is a scalar function. That's why this result over here is a scalar function, which is the curly bracket of A and B, by definition. Now, for I is equal 1 to n, okay? That's clear. Then I can write I, attention now, I is dummy index, Qi, Pi, Pi, Qi. You see, a dummy. Now, you can expand this for I is equal 1, 2. You just set over here. This is plus, this is minus, minus. That's a summation, Einstein summation. You see, the Einstein notation. So then you can write, you see, this curly bracket between A and B. As I said, in the literature in general, you set F and G, okay? And that's the result. Now, this is a 2 degree of freedom Poisson bracket. Attention now, the result is a scalar function. As I said, when I multiply all these matrix dimension, okay, this is row, in this case, 1 by 4, this is 4 by 4, this is a column, 4 by 1. If you multiply, this is a linear algebra multiplication, that's quite easy for you. So you just, the result, this leads to a scalar function. So, this case, curly bracket, Poisson's bracket, the result is a scalar function. See, there's a scalar function. And also I would like to remark that Qi, Pi, okay, are independent variables. Okay, that's it. So next video we will show derivation of the key properties of symplectic geometry. See, and also don't forget to go in the lecture 2 and see the description. It's very interesting for you to familiarize with the symplectic geometry. Okay? It's applied to classical physics and classical physics and classical mechanics. You see, and this use only intrinsic geometry. Okay, and the tools for this is the exterior algebra. Exterior algebra is the tool for the intrinsic geometry. Okay, that's it.